we're taking a coil of wires. So you have to kind of imagine that this is a coil of wires like I passed out in class. So you kind of looked at it, and I'm looking at a cross section of it. So I'm just shearing it off, and this is a cross section of the wire. So the wire here is connecting to the wire up there, and this is coming back down to here, and then it's going back up to there, and then this is coming down to here, and then it's going back up to there. You getting the idea of what it is? You're seeing how it's supposed to look. So that if you're paying, even remote attention, all of these wires will have current coming out of the board because it's a cross section. So if we look at the way and I'm just making up a direction for the current, but we're going to say that this is the out of the board direction of current. And yes, I'm going to draw a dot in each one of these stupid little circles. And you know that means at the bottom, I'm going to draw an X in each one of those stupid little circles too. But each one of these little circles represents one coil of wire. And then down here, the current must be going into the board. So the white portion of what I've drawn is the wires and the direction of current. Oh boy, that's a lot of X's. So again, what we're talking about today is a solenoid. All right, now, this part is going to require some buy-in. And I want to just pick out one of the wires. So I'm going to pick out this wire. Just look at that one for a minute. I know that it is going to produce a magnetic field that is circular around the wire. I also know that magnetic field is going to get smaller as we get further away from the wire. So as I look at just that wire for a moment and use the right-hand rule, I know that the direction of that magnetic field will be this way and this way. You guys following what I'm doing? Getting the idea of what I'm doing? All right. I'm going to also now take a look at this wire right there, the one that's on top, that's directly across from the coil that we started. And we're going to look at that one specifically. And again, I know that the magnetic field around that wire is similarly structured. No, not like that. Oh, Mr. Shelton, you're terrible. Just terrible. I don't understand what I've done wrong here. There we go. So I'm making this one in blue purposely to draw a little contrast. All right, so you see my blue circles there? Magnetic field, because this current is coming out of the board, the magnetic field is going to be this way. So when I start considering the arrows I'm going to draw for that, this way over here, and this way over here, and this way, and this way, and this way, and this way. All right, so do you guys have something similarly drawn for yours? So here's the first thing I want to talk about with solenoids, is if we say, look on this part of the solenoid, do you notice clearly that the magnetic fields appear to be in opposition to each other? You guys see that? So this is outside the solenoid on the top. And outside the solenoid on the bottom, we get a similar opposition. So the two magnetic fields are in opposition to each other. Do you guys see that okay? So outside of the solenoid, the magnetic fields are canceling out. But inside the solenoid, do we see that the magnetic fields are contributing to each other and are aligned? So the first thing I want to promote is that a solenoid is clearly going to give us an enhanced magnetic field down the center, but is also going to disrupt the magnetic field on the outside. Now, the parallel plate did that to electric fields, right? Parallel plate capacitor, when one was positive and one was negative, we got contributing contributions between the plates, but canceling out outside the plates. So, one of the statements I'm going to say before we use Ampere's law is that I believe if we are careful about our placement of our Amperian loop, the magnetic field on the outside of our solenoid, especially towards the middle, is probably going to be zero. But we're going to have to make a couple of assumptions for this to work. First, I want my my coils to be very close together, and I want this to not have a particularly large diameter, so that the distance, I guess I want to use the word distance, for the blue lines and the red lines here are close enough where both magnetic field contributions are nearly equal and therefore cancel out. So we're talking about a long, somewhat skinny solenoid. Does that make sense? So this brings the word ideal to the forefront, right? The idea that we're talking about an ideal solenoid, and we're going to have to take some liberties here to call it an ideal solenoid. I hope you kind of appreciate that just a little bit. All right, we all good to go? All right, so in order for us to study an ideal solenoid, I'm going to make two other assumptions, aside from the fact that it's skinny and long. The next assumption I'm going to make is that the magnetic field is relatively uniform inside the solenoid due to the fact that I have all these contributions from every other coil. So the coil just to the right of this one here is contributing enough magnetic field in similar directions so that the magnetic field through the center and even here and here are all aligned to the right, and I get a net magnetic field that is this direction inside the solenoid. That make sense? All right. I'm going to choose an Amperian loop that I think makes sense, but I'm going to choose to draw my loop near the middle of my solenoid so that I get the maximum amount of uniformity. That suggests something that you guys should probably put in your notes now, that near the edges of a solenoid, this is probably going to break down. So again, edge effects take place in solenoids too. So I think this will work great in the middle of our solenoid. I think it's going to work like garbage towards the edge of our solenoid. So I'm going to stick in the middle because I don't want to make my integration particularly hard. I'm also going to, for the next few moments, get all these circles out of my way if I can. Maybe. There. And just say that I've got a magnetic field through the center. I know you spent all that time drawing that stuff and then I just erased it all, but that's okay. So, my Amperian loop, I am interested in the magnetic field inside the solenoid. So I want my Amperian loop to be inside the solenoid. But I have to enclose current to use an Amperian loop. So I know that part of my loop needs to be outside the solenoid. So I'm going to choose an Amperian loop that is rectangular in nature. In that way, I can exploit the symmetry a little bit better. There, that's my Amperian loop. I'm careful to try and make sure that I am, collecting it around some current wires. So I'm not going through a wire, so I'm going between the coils of a wire. I am making sure that I have a portion of my loop that is inside the region of space where there is a magnetic field, and a portion that is outside the space where there's a magnetic field. Like I said, I made the argument that there's no magnetic field out here, but my magnetic field is nice and strong in here. I'm using a rectangle purposefully because I believe that this portion of my loop will be perpendicular to the direction of the field, right? Because I'm going to be doing a dot product, and I want to make sure that I'm either, completely perpendicular to the field or completely aligned with the field. So I want my dot product to work out for me as easily as possible. So I have two parts of this loop that I know are perpendicular to the field. So when asked to do this, when we're drawing our Amperian loop, we're picking a rectangle so that our summation is easier to do. So you would not draw an oval, you would not draw a circle. That'll defeat the purpose. You want your Amperian loop under these circumstances to be rectangular. All right, my Amperian loop. I'm going to define some parts of this loop. I'm going to define this to be W. So it is 2W high and I'm going to define this to be L. And I hope that it's obvious why I made it 2W is because part of my loop is inside the region with the magnetic field and part of my loop is outside the region with the magnetic field. Does that make sense so far? I'm going to label some corners here, A, and the wire right here, B, right there in the center, C, D, E, right there in the center, and F. Everybody see why I'm labeling it this way? If not, you'll understand. I'm going to take my Ampere's law and I'm going to break up the summation into 1, 2, 3, 4, 5, 6 parts. Because 3 of those parts are automatically 0 because they're outside the region of space with the magnetic field. And 3 of those parts are inside the region with the magnetic field. So you understand why I'm doing it this way? All right. Part of your issues with the way you explain things is that you don't explain them well. So I'll remind you that one side of Ampere's law is a summation, and I'm adding up the length. In summing the length, the direction of that length is important and vital to the sum. That's what the dot product is doing here. So I see that I will be taking this sum and breaking up into 6 parts. So I'll have A to B, that's one of the parts. But I know that one's going to be 0 because the magnetic field in that region is 0. But also B to C, which is another part. It's inside where the magnetic field is. But I'm trying to be very expressive here that that's going to also be 0. But it's not 0 because the magnetic field is 0. It's 0 because of the dot product. So when we're explaining ourselves, we need to explain it thoroughly and be careful. So in your notes right now, I'm actually going to pause long enough for you to walk around the loop and talk about in your notes why each part either contributes or doesn't. So, and I'm going to explain why each one does or doesn't. And it's going to be long-winded, but I want your notes to be helpful because I've been getting that complaint a lot this year. So there's going to be, I'm not going to write it down, but there's going to be A to B, B to C, C to D, D to E, E to F, and then F back to A. So we know A to B will be 0 because the magnetic field is 0. B to C will be 0 because the dot product. C to D is not going to be 0. That's the one. That's the one that contributes. That's the one I need. That's the one I'm going to use to figure out the size of the magnetic field because it's aligned with the magnetic field and it's in the region of space where there is a magnetic field. But D to E, 0. Why? Dot product again. E to F, 0 because it's outside the magnetic field. There's no magnetic field in that space. And F to A, 0 again. Why? Outside, where there's a region of space that there's a magnetic field. So all of these are 0 because there's no magnetic field out there. But these two are 0 because of the dot product. All right. There, gave you more than enough time. So, hopefully, because I gave you all that time, I save myself the ability of not having to write out 6 different integrals. I'm going to write out 1. Right? I'm only going to care about the fact that I want to integrate from C to D, B dot ds. And I'm losing the vector symbols, and I'm going to lose the dot product, and I'm going to put cosine 0 degrees. Because I'm going to go in the direction of the magnetic field. I'm going from C to D. So that's the direction of my Amperian loop's integration is this way. So it's perfectly aligned with the magnetic field. We all good? All right. Now, this has to equal mu naught times I enclosed. I know that my rectangle actually encloses an exact number of loops. I'm not going to count them. I'm going to say that there are n loops of current. But I want to be able to apply this to any solenoid. So I'm just going to say the number of loops is n. We all okay with that? The way we do this is a little particular. I'm using capital N. Okay? You'll understand why in a minute. So I'm going to write mu naught capital N times I, whatever the current is passing through one loop, because we know the current in one loop has to be the same as the current in all the loops, right? It's one continuous wire that's just been formed into a bunch of loops. This is going to equal, I'm pulling the B out of the integral because we know it's constant along that line, and I will just have the sum from C to D of a length ds. Now, the math portion, pretty easy now, right? The length from C to D is the length of my Amperian loop, so that's just B times L. And again, mu naught Ni. That's it. You've done it. You've used Ampere's law. Well, I have. And if you've taken notes, you have. It was a closed, bounded integral because we walked around the entire loop, but we only had to integrate for one small piece of it because most of the contribution was 0. When I solve this for B, group yours the way I group mine. Mu naught N over L times I. This is the magnetic field inside a solenoid, and this is known as the loop density. Sometimes written as mu naught little n times I, where little n is wraps per meter. I wouldn't memorize it that way. I would memorize it as capital N over L. And note that that is the loop density. It's a number of loops per meter.